Hello and welcome everyone to my channel Code with Ease. This is the second video as part of the binary search algorithm. In the first part, we discussed about an overview of linear search and binary search algorithm, how the algorithm works. We also did a dry run on an example, and we also discussed on this optimization algorithmic paradigm, decrease and conquer. In today's session, we are going to discuss the code implementation, both iterative and recursive way of implementing the algorithm, and at last, we are going to discuss the performance of binary search algorithm. So now let's see the code implementation. Hi, here's a brief introduction for the ones who are new to the channel. The objective of Code with Ease is to make problem solving in programming simpler. If you are someone who wants to become a great developer and wants to level up their skills, data structures and algorithms is indispensable and you need to form a solid foundation of that. And this is exactly where we come in. Because we post topic wise video explanations in Java on various coding interview questions that can not only help to crack the coding interview, but also help to improve and refine the problem solving abilities as a developer. And finally, here is the USP of our channel. We code every solution live, we do not copy paste code snippets. We start off by clearly defining the problem statement, the given inputs, the required output, time and space complexities. We also then discuss the brute force way of solving any question without jumping onto the solution and then gradually move on to the optimal solution. We try to use online whiteboarding wherever applicable to explain the approach and the concepts. So that is all about us. So if you guys also want to be a part of this journey, do support us by subscribing to the channel. So with that, now let's get back to the question. So now let's start with the code changes. So this is the array that I've taken, and this is the target element which we have to search for in this array and return the index of that. So I've used this built-in method to sort the array, as we have learned that in binary search algorithm, the prerequisite is the array should be sorted. Now with that, let's start with the code changes. First thing is we define the high and the low pointers as we discussed in the dry run, and then we'll use a loop. Inside this loop, we are going to calculate the midpoint, which we usually do by calculating low plus high. This is the older way of calculating mid, but as we learned in the optimization technique, the correct way of writing this should be low plus high minus low divided by 2. This is to avoid any kind of overflow exception. If ARR of mid is equal to the target, return mid, as we are going to return the index only. Else if ARR of mid is less than the target, then we will recalculate the low as mid plus 1. And finally, in the else block, we will high will be equal to mid minus 1. Outside the loop, we are supposed to return minus 1. This is the condition when if none of the elements matches the target element that we are trying to look for, we have to return minus 1. So that's all. Let's try to run this. So this is index. So this is index 3. Now you guys might be wondering why, because 4 is appearing at the end of the array. Remember that we had sorted the array. So I'll just print out this array itself so that we can visualize what is the actual position of this element 4. As we can see in the sorted array, the position of 4 is the third index. That is why we have got 3. Now we can try to change the target. Let's say I'll give the target as 21. Seven, 0, 1, 2, 3, 4, 5, 6, 7. So this is the 7th index. This is index number 7. So we have got. Now let's try to give a target, an element which is not at all there in the array. Let's see what does it return. Like I said, if the element doesn't appear in the array, we have to return minus 1. So this is the code implementation of the normal binary search algorithm. Now we will see how to write the code for binary search using recursion. So as we know, in case of recursion, there are two things. First is the base case and the main body in which the actual recursion happens, where the function is getting called again and again. So in this case, the method's parameters are changed a bit. So apart from the array, we are also passing in the low and the high pointers. Why are we doing so? Because as you guys can understand from the iterative way of solving this, where is the algorithm of binary search actually coming into play? It is in these two conditions actually, in which we are manipulating the low pointer and the high pointer. Either we are making the low pointer go forward or we are making the high pointer come backward, which also means that in every iteration, the values of the low and the high pointers are changing. So in order to replicate the same scenario in case of the recursion code, we also have to play around with the low and high pointer in every iteration, or better to say in every recursive call. Because we want to change the values of high and low in every recursive call, that is why I've kept these two as the parameters. Now let's see how can we start with the code change. I'll leave out the base case as of now. I'll just focus on the main body. So we'll start off with this, calculating the mid. So at first we have to calculate the mid. What is the core logic which is unchanged? It is this portion. Calculating the mid, and then based on the position of the mid, taking a call whether we want to manipulate the low pointer or the high pointer. All of that remains the same. Now, once we have the mid with us, and once we have this condition where ARR of mid is equal to target, we will return mid, fine. But these two conditions will still remain the same, but in this line, we will have the actual change. What we will do, in this we are going to do the actual recursive call. So we'll call this method using the same parameters for ARR, but in case of low, we will now say mid plus 1. So our new low is going to be mid plus 1 for the second condition. High will remain unchanged and target will also be as is. So this is just 2-line change that we have to do for the main body in case of recursive code. Similarly, for the else part, the low will remain unchanged. Only the high will become mid minus 1. So now let's come to the base case. What is base case? The condition in which the recursive call should stop. In the iterative code, when were we trying to break the loop? This line is the condition when we were trying to break the loop and we were coming out of it, which means when low is less than equal to high, that is the point where we should be breaking the loop. So same thing we are going to use in the base case also, where we will check if low is if low is greater than high at any given point in time, we have to return minus 1. Why? Because if the element is already found, the mid will be returned over here. In the event where the target element itself is not found in the array is when it is going to execute this base case, and then we will return minus 1 because the element is not found. Now let's try to run this method. So I've changed the target to 6 and we are running this new method. 4 is returned because 6 is at the 4th index. Now we'll change this to a different target which does not even exist. Minus 1 as expected. So with that, we wrap up the code implementation of both binary search using iteration and also using recursion. Next up, we will see the performance analysis of binary search algorithm. So we are going to wrap up today's session by discussing on the performance of binary search algorithm, in which we are going to discuss about the time and the space complexity. When it comes to time complexity, there are 3 types: the best case, worst case, and average case. Best case complexity for binary search will be order of 1, which is constant because, so when will the best case arrive? When the ARR of mid, the first condition which we were having, when the mid element itself is the element that we are looking for. So we don't have to traverse the entire array. Whenever we are calculating the mid, at the very beginning only, we are able to get the element that we are looking for. So in that case, the time taken will not be dependent on the input size. That's why the time complexity will be constant. But in case of worst case or average case is when the element is lying at either ends of the array. So that's why it's going to be order of log n. And the same goes for average case. Order of log n because, as we discussed earlier, in binary search algorithm, the problem space or the search space is being divided by half repeatedly. So first, if the input size is n, then it becomes n by 2, then it becomes n by 4, and so on. Because of that, we are able to achieve logarithmic time complexity. There's a way to derive the mathematical formula. You can let me know in the comments if you want me to discuss more about how to derive the time complexity of binary search. Coming to the space complexity, since we are using 3 pointers, the high, low, and mid, which is again not dependent on the input size, that is why the space required is constant. So that's all about the performance of binary search algorithm. Do let us know in the comments below if you guys have any questions or doubts, or you want to share any feedback on this video. If you have enjoyed the session so far, do hit the like button so that this can reach out to many more people. And if it does, it just gives us enough motivation to put out more such content. Also, if you are looking forward to more videos like this, please don't forget to subscribe to the channel and press the bell icon next to the subscribe button to never miss an update on our upcoming videos. Thank you so much for watching.